Very good afternoon. I am Rahul, Waghmare, Assistant Professor in Department of Mechanical Engineering, Jindal Institute of Technology, Nagpur. And my today's topic is linear variable differential transformer. So let's see exactly that linear variable differential transformer (LVDT) and how it works. So here it's a transducer. So we can say it's a transformer, or sometimes we can say it's a transducer. Why? Because here it's a device. So what exactly a transducer? It's a device which converts one physical parameter onto the another physical parameter. So this particular device is known as the transducer. So let's say about LVDT. So basically LVDT used for the measurement of a displacement. Now it works on the principle of mutual inductance and basically used for the measurement of a angular as well as linear displacement. So let's see what exactly we are having onto the LVDT and how it works. So basically it consists of two coils. A very first one is the primary coil and the second one as a secondary coil. And now in between this primary and secondary coil we are having one movable coil. And now this is the shaft which is to be connected to the system where we can measure the displacement. Let's see one by one. So here the mutual inductance or electromagnetic inductance, how it works. So here the formula for inductance capital L is equals to phi upon I, where phi is nothing but it's a magnetic flux, where I is the electric current. As we know, as per according to the inductance, so whenever we are supplying an electric current onto the circuit or onto the wire, so the magnetic field are to be induced. Okay, so this magnetic field, suppose we are passing to the another coil, so again we are getting the electric current. So that basically principle we are using to get the deflection onto the system. So here that electromagnetic induction and now onto the LVDT. So we are having initially as a primary coil. So let's see, this red color line indicates a primary coil in which they are supplying an electric current, is having around 230 volt, is having a voltage potential difference and is having a 50 hertz of frequency. So this electric current are supplying onto the primary coil. So it circulates like this and we are getting exit from this particular coil. So because of the supplying of electric current, it creates a magnetic flux. So here onto the left and right hand side of this particular primary coil, we are having a secondary coil. So this secondary coil, both are connected to the same connection. So let's see how it is to be connected. So these two coils are to be connected in a series connection. So let's see how it connected. So here is the input to the secondary coil, goes like this. Okay, it exits from here and now again it is to be connected series to the second coil. This here, these are the secondary coil consists of two coils. One is this one and second is this one. But now let's see the arrangement. The initial, suppose we can say that it's a phase of a first coil. So it goes like this and it is connected to the second coil. So here the direction of this coil is from this one direction to this one direction. It's from right to the left side, while the direction of this particular coil is from left to the right side. This nothing but we are getting, means whenever we are getting that induced EMF, so that induced EMF it is onto the opposite direction because of the opposite direction of the secondary coil. So here is the construction and circuit diagram of LVDT. So here basically in between these two coils a soft core iron is to be present. So here it's a soft iron core which is to be present inside the primary as well as these two secondary coils. Okay, and now this is the shaft to be connected to the system where we just have to change the displacement. So here this particular core are to be present at the center part. So whenever we are supplying an electric current to the primary coil, let's say the circuit diagram. So here is a primary coil which is to be connected to the AC volt. Okay, AC volt. And now these are the two secondary coils are to be connected series. So this is the first coil. Okay, to the connected to secondary coil in a series manner, but now the directions are opposite. So here and now here we are getting the difference in output from this particular coil. So let's see what happened exactly onto the system. So when that particular core is exactly at the center, so the EMF is induced. So EMF is induced onto the primary coil, and because of that particular EMF, we are getting again we are getting that EMF onto the secondary coil. But now that core is to be present exactly onto the center, So that's why the EMF produced by the secondary, these two secondary coils are exactly same. So therefore we can say that here the Vs1 minus Vs2 is exactly equals to 0. Is the difference in voltage in case of a primary coil as well as secondary coil is exactly 0. And now nothing but when this particular difference is exactly equals to the 0, so what happened? So we can say that is equal to the 0. So Vs1 is exactly equal to Vs2. So what happened here? So when Vs1 is exactly Vs2, there is no deflection. This now the core is to be exactly present onto the center, then there is no deflection. But when this particular soft iron core are to be moved to the right side as well as onto the left side, take an example. Suppose if the core is to be moved onto the right side, so what happened? So the EMF induced or the voltage induced onto the secondary coil. So that is Vs2 is greater than Vs1 because here the core are in between primary as well as secondary coil. So the EMF induced onto the secondary coil is compared to be more as compared to the Vs1. And because of that particular difference onto the voltage, so that difference onto the voltage, so we can use that particular difference onto the voltage for the measurement of a displacement. So this is basically it's a working and construction of a LVDT. So these all are the details of a LVDT. So primary, secondary coil, when we are supplying onto the current on both the coils, so we are getting some EMF and everything, and because of that we are getting some deflection. So again, this working I already explained how it works. So this is at the null position whenever we are not getting any deflection. But now when that particular core artery shifts, so we are getting some deflection, and now that deflection is to be used for the measurement of a displacement. So let's see what are the advantages of an LVDT. So it's a high range. So measurement of a displacement is ranging from 1.25 mm to 250 mm. So it's a very high range for the measurement of a displacement. So it's a frictionless. There is no contact between the core as well as coil. So that's why we can say that there are no such parts are there which are in tear, which are in wear and tear. So resulting we are getting higher mechanical efficiency or mechanical life. So here we are getting higher output as well as higher sensitivity. So can we tolerate high degree of shock and vibrations? So here we are using this particular, because of that we are using this particular instrument where we are having higher shocks and vibrations are there. It's a simple design in construction, and the most advantageous part is it will require less than 1 watt electric power. But now as well as there are some disadvantages there. So large displacement required for appreciable differential output. So nothing but for a very small displacement we cannot use this particular system. So basically this is the drawback of a LVDT. So sensitivity to stray magnetic field with shielding will be provided. So